In the silent depths of a July night, in the year 1994, a small point of light flared into existence on the face of a world that was not our own, a signal of destruction traveling 500 million miles across an empty ocean of space to reach the eyes of a species just learning to look. This was no ordinary star, no predictable pulse from a distant sun. It was the death rattle of a mountain, the final, furious testament of a comet obliterated against the atmosphere of a giant. For the first time in all of human history, we were not merely chroniclers of the static heavens, not just interpreters of ancient light from events long concluded. We were witnesses to real-time, cosmic-scale violence. We watched a demolition we did not cause, a spectacle of pure celestial mechanics unfolding with the terrible grace of natural law. The gaze of our world turned upward that July, not in search of ourselves, but in witness to a truth we had long suspected yet never seen so vividly illustrated, that the serene clockwork of the heavens is a profound illusion, a temporary calm between storms of creation and destruction that operate on timescales far beyond human memory. On a canvas so vast, our entire civilization is but a brushstroke. The event was a punctuation mark in the solar system's long whispered narrative. A sentence ended not with a quiet period, but with an exclamation point written in fire and darkness across the banded atmosphere of Jupiter. And for the astronomers who watched, their instruments humming in observatories scattered across the spinning Earth, it was a moment of profound duality. The thrilling validation of prediction and calculation, coupled with the humbling, chilling realization of our own fleeting, fragile place within a dynamic and often violent celestial arena. This was not a theoretical exercise, not a simulation running in the sterile environment of a supercomputer. This was real. The comet, known to science as Shoemaker-Levy 9, was real. Its fragments, each a mountain of primordial ice and rock, were real. Their collision with the largest planet in our solar system was devastatingly, magnificently real. And the data that streamed back to Earth, captured by our mechanical eyes in space and our glass ones on the ground, would irrevocably alter our understanding of our own cosmic neighborhood, rewrite chapters of planetary science, and awaken a dormant, ancestral awareness to a danger that had always lurked, patient and silent, in the dark between the stars. To comprehend the true scale of this event, one must first step back from the notion of a planet and instead contemplate a sovereign realm. Jupiter is not merely a planet, it is a solar system in miniature, a failed star that holds dominion over a vast kingdom of swirling moons and intense radiation, a gravitational titan whose influence shapes the architecture of our entire planetary family. Its mass is a staggering 2.5 times that of all other planets in our solar system combined. This immense bulk creates a gravitational pull so profound it acts as a cosmic shepherd, a deflector, a titanic anchor around which the intricate dynamics of asteroids and comets are orchestrated over millennia. Its atmosphere is a seething, chaotic ocean of hydrogen and helium, racked by storms that endure for centuries, the most famous being the Great Red Spot, an anticyclone of such ancient fury that it could swallow our Earth whole without a trace. To stand upon its cloud tops, if such a fantasy were possible, would be to experience a gravity 2.5 times stronger than our own, a pressure that would crush any vessel into oblivion, and winds that scream at speeds exceeding 400 miles per hour. This is the Colossus that, in July of 1994, found itself directly in the path of a celestial bullet train, a target of monumental proportions. The story of this collision does not begin with the brilliant flash of impact, but a year earlier, under the tranquil, starlit dome of the Palomar Observatory in California. There, the astronomer Caroline Shoemaker, her husband Eugene Shoemaker, a geologist who had revolutionized our understanding of impact craters on Earth and the Moon, reading violence in ancient stone, and their colleague David Levy, a dedicated and patient comet hunter, were engaged in the meticulous work of scanning the heavens. Their tool was a specific type of telescope, designed not for deep static beauty, but for the detection of motion. The subtle, telltale shift of a faint, fuzzy speck against the fixed backdrop of distant, timeless stars. On the night of March 24, 1993, their photographic plates revealed something peculiar, something that defied immediate classification. It was not a crisp point of starlight, nor the soft glow of a distant galaxy. It was a strange, elongated smudge near the bright limb of Jupiter, a luminous smudge that refused to resolve into a single, defined nucleus with a trailing tail. Instead, it appeared as what would later be described as a barred comet, a luminous string of pearls, a line of distinct fragments trailing through space in a gentle, mournful arc. It was, as Eugene Shoemaker would later say with characteristic clarity, like a comet strung out on a string. This peculiar fractured object was designated Shoemaker-Levy 9, the ninth periodic comet discovered by the team, though it was unlike anything they had ever seen. Immediately, its orbit became the subject of intense, urgent calculation. The initial revelation was startling. This comet was not orbiting the Sun in a conventional, graceful ellipse. Its path was tightly, precariously bound to Jupiter itself. Shoemaker-Levy 9 was a captured object, a rogue traveler from the outer darkness that had, at some point in the perhaps recent past, ventured too close to the gas giant's immense gravitational well and been seized, forced into a lopsided, elliptical dance around the planet rather than the Sun. This in itself was not unprecedented. Jupiter is known to possess a scattered retinue of irregular moons thought to be asteroids and comets captured in a similar, forgotten fashion. But Shoemaker-Levy 9 was different. It was already broken. The string of pearls was not an illusion of perspective. The comet's very nucleus had been torn asunder. The culprit was Jupiter's immense tidal force, the same force that twists the Moon Io into a world of perpetual volcanic agony. On a previous, closer approach to the planet, the comet had strayed inside its Roche limit, that critical mathematical distance within which a celestial body's own gravity can no longer hold it together against the differential, stretching pull of a larger neighbor. Just over 40,000 kilometers above Jupiter's cloud tops, the giant's gravity had quite literally pulled the comet apart in a slow-motion act of cosmic violence, stretching it and shredding it into a train of distinct fragments, like a handful of gravel scattered along a shared, doomed trajectory. The orbital calculations that followed this discovery delivered an even more profound shock, a chill that ran through the astronomical community. The comet's path was not just elliptical, it was extraordinarily, almost impossibly, eccentric. In the language of orbital mechanics, eccentricity is a measure of how much an orbit deviates from a perfect circle, expressed as a number between 0 and 1. A perfect circle has an eccentricity of 0. An ellipse, like Earth's gentle orbit, has a low eccentricity around 0.017. A highly elongated ellipse, one that stretches far out into the darkness before swooping in close, approaches an eccentricity of 1. The orbit of Shoemaker-Levy 9 was calculated to have an eccentricity of over 0.998. This was not merely an ellipse, it was a hairpin turn written in the fabric of space-time, a trajectory so extreme that its closest approach to Jupiter, its perigove, was terrifyingly intimate, while its farthest point took it only just beyond the orbit of some of the planet's outer moons. And as astronomers refined their models with cold, unforgiving mathematics, a chilling certainty coalesced from the numbers. The comet's next perigove, its next closest pass by Jupiter, scheduled for July of 1994, would not be a pass at all. The mathematics were unambiguous, the celestial mechanics unequivocal, the orbit intersected the cloud tops of Jupiter itself. The fragments were on a direct, unalterable collision course. The prediction was no longer a question of if, but of when and how spectacularly. For the first time in history, humanity was going to watch, with foreknowledge and preparation, a major interplanetary collision. We had a front-row seat to an apocalypse, not our own. The anticipation that built in the astronomical community over the ensuing 16 months was a palpable force. A unique mixture of intense, disciplined scientific fervor and sheer, childlike wonder. Every major telescope on Earth, and more importantly, those liberated from our atmosphere in space, was tasked with observing the impending event. The Hubble Space Telescope, then recently repaired and its visionary capabilities corrected by a pioneering shuttle mission, was poised to capture unprecedented detail, its electronic eyes focused on the giant. Ground-based observatories, from the dry peaks of Chile to the volcanic summits of Hawaii to the isolated mountains of the Canary Islands, prepared for the long vigil, their domes poised to open on a history-making night. But a significant, frustrating problem presented itself, a twist of celestial geometry. The impacts, dictated by the comet's incoming trajectory, would occur on the far side of Jupiter, the hemisphere facing away from Earth. The initial moments of impact, the flash of energy, the rise of the first plumes, these would be hidden from our direct view by the colossal, obdurate bulk of the planet itself. It was a cruel twist of fate, offering a front-row seat to a theater where the curtain would rise on the wrong side of the stage, leaving Earth in the audience for the second act, forced to wait for Jupiter's slow rotation to reveal the aftermath. Yet, the cosmos occasionally bestows gifts of profound serendipity, aligning its distant players in a moment of observational fortune. Unbeknownst to the discoverers of the comet, a robotic ambassador from Earth was already on a long, silent journey to the Jovian system. The Galileo spacecraft, launched in 1989, was still a year away from its primary mission of orbiting Jupiter, but it was fortuitously positioned in interplanetary space, with a direct, unobstructed line of sight to the impact zone. Its instruments, designed to study planetary atmospheres and magnetic fields, could be repurposed in a moment of unprecedented opportunity to witness the cataclysm firsthand. Further afield, the Ulysses spacecraft, on a mission to study the Sun's polar regions, was commanded to turn its sensors toward Jupiter. Even the venerable Voyager 2, by then 17 years into its journey and over 44 astronomical units away, far beyond the orbit of Pluto, sailing into the interstellar void, was enlisted to listen for the subtle radio emissions generated by the violent impacts. Humanity's scattered mechanical senses were aligning across the solar system, forming a makeshift but powerful network of perception to capture an event no human eye had ever seen, creating a symphony of data from a point of silent cataclysm. The bombardment began with a silent flash in the void on July 16, 1994. Fragment A, the first in the grim line of 21 major pieces, plunged into the Jovian southern hemisphere. From Galileo's lonely vantage point, the event was a silent, brilliant catastrophe. A fireball, a term too small for such grandeur, erupted with unimaginable ferocity. Temperatures at the core of the initial flash were estimated by instruments to reach 24,000 Kelvin, over 4 times hotter than the surface of our Sun. This was not merely a kinetic impact. It was a transformative release of energy where the sheer velocity of the comet fragment, traveling at approximately 60 kilometers per second or 216,000 kilometers per hour, was converted instantaneously into heat, light, and titanic shock waves that radiated outward. The comet, a fragile mixture of water ice, frozen gases, and ancient silicate dust, did not simply bury itself in the atmosphere. It vaporized, it exploded, it excavated a wound in the sky. The fireball, a superheated bubble of gas and vaporized comet and churned Jovian atmosphere, rose like a furious, incandescent mushroom cloud, punching upwards through the stratified atmospheric layers with the force of a world-ending weapon. What followed was perhaps even more astonishing, a phenomenon that stretched the very definition of atmospheric physics. As the initial fireball cooled and expanded, it acted like a colossal piston, lofting material from the hidden depths of Jupiter's atmosphere high above the familiar cloud tops. Plumes of dark, dusty debris, rich in exotic compounds, ripped from the comet and from Jupiter's own hidden chemical reservoirs, were catapulted to altitudes of over 3,000 kilometers. To visualize this scale, one must imagine a column of material reaching from the surface of the Earth to well beyond the orbit of the International Space Station, a tower of cosmic debris so tall it would span the continent of Australia from north to south. And then, under the relentless, inescapable pull of Jupiter's own gravity, this lofted material began its long, terrible fall back down. The re-entry of these plume particles created a secondary holocaust, a planet-wide rain of fire as countless pieces of debris heated the upper atmosphere upon their descent, turning vast regions into a radiating furnace visible across the solar system. The total energy released was staggering, a number so vast it loses all meaning in human terms. The combined force of all 21 impacts was estimated to be equivalent to 300 million megatons of TNT. To put this in a slightly more graspable, if no less terrifying, context, the largest nuclear device ever detonated by humanity, the Soviet Tsar bomber, had a yield of roughly 50 megatons. The Shoemaker-Levy 9 event released the energy of 6 million such bombs, concentrated over a few days on a single giant world. As Jupiter's stately rotation brought the wounded southern hemisphere into the view of Earth's waiting telescopes, the instruments captured the aftermath, and the world saw the scars. The pristine, banded face of the giant was marred, tattooed with violence. Huge, dark smudges, each one the scar of an impact, dotted its atmosphere like a pox. They were not simple bruises, but complex, evolving structures of ejected material, rapidly stretching and distorting under the shearing winds of the fierce Jovian jet streams. The largest of these, created by Fragment G, which struck on July 18th, was a monstrous, dark eye roughly 12,000 kilometers across, the diameter of Earth itself. For a time, this new temporary feature was more prominent, more visually arresting than the ancient Great Red Spot, a stark and dominant blemish on the face of a god. These scars were not superficial stains, they were temporary windows into the abyss. The plumes had dredged material from layers of the atmosphere usually hidden from view far below the bright, reflective decks of ammonia ice clouds. Spectroscopy, the exquisite art of deciphering the chemical fingerprints of light, was performed on these dark clouds. The results were a scientific treasure trove. Astronomers detected molecules like diatomic sulfur and carbon disulfide, which must have been forged in the intense alchemical heat of the impact fireballs. More crucially, they found the clear, unambiguous signatures of heavy elements: silicon, magnesium, iron, the very stuff of rock and dust, the primordial building blocks of terrestrial planets like our own. These were the remains of the comet's rocky core, splashed across the Jovian sky for all to see, a direct sampling of a visitor from the deep cold. But one detection was particularly intriguing and has fueled sophisticated scientific inquiry for decades since the event. Water. Significant amounts of water vapor were found swirling in the impact plumes. This was a puzzle that reached into the heart of Jupiter. The comet itself contained water ice, of course, a fundamental component of its being. But the quantities observed seemed to suggest another, more enigmatic source. Perhaps the impacts had excavated deep enough, with enough force, to reach a layer in Jupiter's own atmosphere where water vapor, trapped beneath a colder, drier cloud deck, could exist in abundance. Or perhaps the fantastically complex chemistry of the impact site itself, a cauldron of unthinkable pressure and temperature, synthesized new water molecules from raw atomic ingredients. This question became so central, so compelling, that one of the primary science goals of NASA's Juno mission, which arrived at Jupiter in 2016, was to map the distribution of water in the planet's deep atmosphere, a direct and profound legacy of the questions raised by those dark, watery plumes in 1994. Beyond the immediate atmospheric chemistry and physics, the impacts generated other, more subtle phenomena that spoke to the scale of the disturbance. The colossal releases of energy sent powerful shock waves racing horizontally through the Jovian atmosphere like ripples on a pond of gas. These were detected as concentric rings of disturbed clouds expanding from the impact sites at speeds of around 450 meters per second, visible for days as they propagated across thousands of kilometers, a visible pulse of trauma. Furthermore, the violent events generated intense, short-lived bursts of radio emissions picked up by the distant ears of Voyager 2 and other sensitive instruments, caused by charged particles being accelerated in the turbulent, magnetized aftermath of each strike. Even Jupiter's vast magnetosphere, the largest single structure in the solar system, a great magnetic bubble that rings the planet with belts of intense, deadly radiation, was subtly perturbed by the injections of fine dust and ionized gas from the destroyed comet, a temporary infection in the giant's magnetic field. For 6 days, from July 16th to the 22nd, the bombardment continued, a methodical, cosmic pounding that held the attention of the world. Each impact was a unique experiment, a natural laboratory of hypervelocity physics, with results depending on the precise size, composition, and angle of the fragment. Scientists watched, catalogued, and analyzed, their databases swelling with a flood of information that would take years to fully process. But as the last fragments disappeared into the swirling clouds and the immediate spectacle faded from the headlines, a deeper, more profound realization began to settle over the scientific community and the public that had followed the event with rapt attention. Shoemaker-Levy 9 was not just a spectacular show, a celestial fireworks display. It was a message, a stark, unambiguous warning written in the universal language of fire and kinetic energy. It was a telegram from the cosmos, delivered with the force of 6 million thermonuclear bombs, and its text was chillingly clear. For decades, even centuries, the solar system had been perceived by many, both in culture and in science, as a stable, settled, almost orderly place. The planets followed their predictable paths in a grand orrery. The asteroids stayed mostly in their defined belt. The comets were distant, occasional, and harmless visitors from the fringe. The concept of catastrophic impacts was comfortably relegated to the distant, mythical past, to the hypothesized giant impact that formed our moon in a primordial fog of debris, or to the asteroid strike that ended the reign of the dinosaurs 66 million years ago. That event, the Chicxulub impact, was a geological inference, a story told in a thin, global layer of iridium-rich clay in grains of shattered quartz, in the subtle topography of a crater buried under the Yucatan Peninsula. It was history, profound but abstract. Shoemaker-Levy 9 was current affairs. It was the evening news from another world. It demonstrated, in real time and with terrifying, luminous clarity, that the process of accretion that built the planets from dust has not fully ceased, that the solar system, for all its apparent calm, still contains abundant, wandering debris capable of planet-scale violence, that the universe, in its quiet expanses, remains a shooting gallery of unimaginable scale, and the planets, including our own, are the targets. The static portrait of the heavens was shattered forever, replaced by a dynamic and sometimes dangerous movie. This realization had a seismic effect on our planetary psyche, a shift in consciousness as profound as the understanding that Earth orbits the Sun. The term planetary defense, which now encompasses coordinated global efforts to track, characterize, and potentially deflect hazardous near-Earth objects, was born in the intellectual and emotional wake of those July impacts. Before 1994, the systematic search for asteroids and comets that could intersect Earth's orbit was a niche, underfunded endeavor, the pursuit of a dedicated few. Afterward, it became a recognized priority of space agencies and governments. Influenced by the advocacy of scientists like Eugene Shoemaker, and with the Hubble images of Jupiter's devastation fresh in their minds, the United States Congress in 1998 officially directed NASA to find 90% of all near-Earth objects larger than 1 kilometer in diameter, objects large enough to cause global catastrophes on our own world. That goal, known as the SpaceGuard Survey, has largely been achieved through relentless observation, and the effort continues with even greater urgency, now focusing on the more numerous, smaller, but still dangerously sized objects over 140 meters in diameter. A global network of telescopes, both professional and amateur, now constantly scans the skies, a direct and pragmatic legacy of watching Jupiter get hit. The hypothetical had become visceral. The dinosaur killer was no longer an abstract concept from deep time. It was a process we had just seen in action on our neighbor, a process with our own address potentially next on the list. This new, sobering awareness also reignited a deep philosophical and astrobiological debate about our place in the cosmos, a debate that touches on the very rarity of life. Jupiter, by virtue of its immense mass and gravitational reach, is often portrayed in this context as a guardian, a cosmic vacuum cleaner. The logic is compelling and aesthetically pleasing. Its mighty gravity deflects or captures many incoming comets and asteroids that might otherwise wander into the gravitational lanes of the inner solar system, striking the smaller rocky worlds. The Shoemaker-Levy 9 event itself supports this narrative. The comet was captured and destroyed by Jupiter, not Earth. Statistical models suggest Jupiter may experience impacts from sizable comets many thousands of times more frequently than Earth does, a constant bombardment that spares us. This perceived protective role has become a key tenet of the rare Earth hypothesis, which posits that the evolution of complex, intelligent life on our planet required a highly specific and fortuitous set of astronomical and geological circumstances, a perfect storm of conditions over billions of years. One of these fortunate circumstances, the argument goes, is the presence of a massive gas giant in the outer solar system, positioned just so to act as a shield, deflecting the relentless bombardment that would sterilize nascent life or prevent its long-term, uninterrupted evolution. Our existence in this elegant view may be partially indebted to Jupiter's periodic, violent sacrifice, its atmosphere bearing the scars so ours does not have to. Yet, the hypothesis is not without its thoughtful critics, and the reality is likely more complex, more nuanced than a simple shield. Some sophisticated dynamical studies suggest Jupiter's gravitational influence is a double-edged sword. While it may eject many comets from the solar system entirely, clearing the neighborhood, its powerful gravity can also perturb objects from stable reservoirs like the Kuiper Belt or the distant Oort Cloud, sending them on new, chaotic, and potentially Earth-crossing trajectories. It may be both a shield and a sniper, a complex gravitational mediator whose long-term role in planetary impact rates is still being carefully unraveled through simulation and observation. The Shoemaker-Levy 9 impacts did not settle this grand debate. Rather, they provided the hard, observational data, the empirical bedrock that made the debate urgent and quantifiable. They forced us to see Jupiter not just as a beautiful banded marvel in a telescope eyepiece, but as an active, dynamic participant in the gravitational dynamics that govern the safety and stability of our own pale blue dot. The giant is not merely a picture, it is a player. The scars on Jupiter, those Earth-sized blots of darkness, were, in the end, transient. Within months, the fierce, relentless Jovian winds sheared them apart, dispersing the dark material until the atmosphere regained its familiar striped appearance, the great storms once again dominating the view. By a year later, only the most sensitive instruments could detect any lingering trace. The giant had healed, bearing no permanent visible mark from the trauma, as if the whole astonishing event had been a dream. But for humanity, the scars on our understanding were permanent, etched into our scientific canon and our species' memory. The event marked a definitive, before and after in planetary science. Before Shoemaker-Levy 9, the study of impacts was largely forensic, based on interpreting crater records, a science of aftermath. After, it became an observational, even experimental science. We had seen the physics of a hypervelocity impact on a gas giant atmosphere played out in real time, with all its complex, terrifying beauty. We had seen the plume dynamics, the shock chemistry, the atmospheric responses. This rich data became the essential benchmark, the gold standard, against which all impact models for Earth, for other planets, for distant exoplanets are now calibrated and tested. The event also served as a poignant personal capstone to the legendary career of Eugene Shoemaker, a man who had dedicated his life to reading the cratered history of the solar system in the rocks of Earth and the dust of the Moon, who had trained Apollo astronauts in field geology so they could read the Moon's violent story firsthand, was, with his wife and colleague, instrumentally present for the discovery of the first impact event humanity would ever watch unfold. He did not live to see the full fruits of the missions and the planetary defense programs his discovery helped inspire. He died in a car accident in Australia in 1997 while conducting crater research, a scientist in the field until the very end. In a tribute of sublime poetry, a portion of his ashes were later carried to the Moon by the Lunar Prospector mission, making him the only human to date to be laid to rest on another world. It is a fitting circular journey for a man who so deeply connected the ancient impact history of Earth and Moon to the ongoing dynamic violence of the present-day solar system, so dramatically and personally illustrated by the comet that bears his name. 3 decades on, the echoes of those July impacts continue to resonate, not as a fading memory, but as an active force shaping our exploration and our vigilance. Every time a new near-Earth object is discovered by a survey telescope and its orbit calculated, every time a mission like DART is launched to test deflection technology by intentionally impacting an asteroid moonlet, every time we point a telescope at Jupiter and remember we are operating in the long shadow and the illuminating light of Shoemaker-Levy 9. It taught us a profound humility, showing us with irrefutable evidence that the cosmos is not a static backdrop for our drama, but an active, evolving, and sometimes dangerous theater in which we are minor participants. It taught us the incalculable value of vigilance, spurring a global effort to find and track the objects that share our space, an effort that is one of the most practical and profound applications of astronomy. And it taught us the power of serendipitous alignment, of having the right telescopes, the right spacecraft, and the right curious minds looking in the right direction at a precise, fleeting moment in cosmic history. It was a lesson in preparedness, in paying attention. That moment was, above all, a gift of perspective, a lens through which to see our place anew. From our distant vantage point, we watched a comet die, and a planet weather a storm of inconceivable power, a storm that would have erased all life on our world. We saw a stark demonstration of the very forces that build worlds and destroy them, forces that are agnostic to the delicate biospheres they shape. In the grand billion-year narrative of the solar system, it was a minor event, a fleeting disturbance on a giant that quickly returned to equilibrium, a small note in a very long score. But in the brief, bright narrative of humanity, it was a profound awakening. It expanded our sense of time, linking the ancient extinction events buried in our own fossil record to processes that are ongoing, visible, and measurable, connecting the deep past to an active present. It expanded our sense of responsibility, pushing us to become stewards not only of our planetary environment, but of our planetary trajectory through a populated and dynamic celestial neighborhood. And it expanded irrevocably our sense of wonder, proving that the universe is capable of staging dramas of such scale and violence that they defy human imagination, yet are ultimately comprehensible to the probing, persistent human mind. As the last fragments of comet Shoemaker-Levy 9 vaporized into Jupiter's atmosphere, they left behind more than just hot gas and dark smudges that faded with the winds. They left a legacy of awareness, a collective memory etched in data and consciousness. We now look at the night sky with different eyes. We know that the serene points of light, the steady wanderers of the planets, exist within a complex and dynamic gravitational dance, a dance that occasionally, inevitably, leads to a collision, a crescendo in the silent music of the spheres. The silence of space is not an indicator of stillness, but of the sheer insulating distance between events. The impacts on Jupiter broke that silence for us, transmitting a message across 500 million miles of void. A message written in plumes of fire and scars of darkness. A message that said, with quiet urgency, "Pay attention. The solar system is alive, with motion, with history, and with consequence. And we, a young species born on a tiny, fragile world in the inner system, are now, finally, beginning to listen." The story of cosmic collisions, however, does not end with Jupiter absorbing a single spectacular cometary barrage. Our solar system, from the sun-scorched surface of Mercury to the icy fringes of the Oort Cloud, is a layered archive of such events, a palimpsest where each crater, each scattered family of asteroids, each peculiar looping orbit tells a fragmentary story of a past encounter, a near miss or a direct hit. To understand the full, deep context of Shoemaker-Levy 9, we must venture beyond that single spectacular data point and explore the broader, ancient theater of impact physics and history. We must journey from the giant planets to our own rocky, life-soaked world, to our cratered moon, and then outward to the frozen frontiers where such comets originate, where they slumber until gravity stirs them to motion. For Jupiter was not the first, nor will it be the last, to feel the sting of celestial debris. It is simply the most obvious and frequent target in our current epoch. Our own moon, that barren and airless companion, stands as the most perfect, untarnished museum of impact history in the inner solar system. Its face, seen with the naked eye as a simple pattern of dark Maria and bright highlands, is in fact a complex, overwritten tapestry of overlapping craters, each one a frozen moment of violence, a recording of an impactor that reached the surface unimpeded by any protective atmosphere. The largest of these, the South Pole Aitken Basin on the far side, spans over 2,500 kilometers in diameter, a scar from an impact so colossal, so early in lunar history that it nearly shattered the infant moon's globe. These craters are not random. Their size and their frequency distribution is a clock, a chronometer written in geology. By counting craters of different sizes on a given surface, planetary scientists can estimate its age. The more craters, the older and longer that surface has been exposed to the relentless statistical rain of projectiles over billions of years. This lunar record tells a consistent story of a violent, chaotic youth for our entire solar system. A period known as the Late Heavy Bombardment, hypothesized to have occurred around 4 billion years ago, saw a dramatic, mysterious spike in impact rates across all the inner planets. The evidence is etched into the ancient, battered highlands of the Moon, Mercury, and Mars. During this tumultuous time, the newly formed planets were still sweeping up the leftover planetesimals from the protoplanetary disk, and gravitational resonances with the migrating giant planets may have hurled a veritable storm of asteroids inward, a celestial shooting gallery of unimaginable intensity. The Earth, with its active geology, its eroding rains, and its shifting continents, has erased most of the craters from this primordial era, but a few deeply buried, ghostly structures remain, like the Vredefort Dome in South Africa or the Sudbury Basin in Canada, silent, eroded witnesses to an age when the sky was full of falling fire, when the very crust of our world was remade by violence. It was a sterilizing violence, but also, perhaps paradoxically, a creative one. The impacts of this era may have delivered not just destruction, but also water and the complex organic compounds, the very ingredients for life, from the water-rich outer solar system to the inner drier worlds like early Earth and Mars. The same process that can extinguish a biosphere in an instant may also have seeded its possibility, a profound and unsettling duality at the very heart of cosmic evolution, where creation and destruction are two sides of the same coin, struck in the forge of gravity. On Earth, the most famous and consequential impact in our relatively recent geological past is, of course, the one that marks the stark boundary between the Cretaceous and Paleogene periods, 66 million years ago. An asteroid, estimated to be 10 to 15 kilometers in diameter, a mountain larger than Everest, struck the shallow seas of what is now the Yucatan Peninsula. The energy released was on the order of 100 teratons of TNT, over 1 billion times more powerful than the atomic bombs that ended a world war. The immediate effects were apocalyptic. A fireball that incinerated everything within hundreds of miles, mega tsunamis that scoured coastlines continents away, and seismic waves that shook the entire globe. But the long-term climatic effects were even more devastating, more thorough. The impact vaporized carbonate and sulfate-rich rock, injecting billions of tons of sulfur aerosols and carbon dioxide into the stratosphere. The sulfur formed a global, sun-blocking haze that collapsed photosynthesis for years, triggering a global winter, an impact winter. The carbon dioxide, once the dust settled, led to a prolonged greenhouse warming. This 1-2 punch of freezing and heating, combined with widespread acid rain and global wildfires, led to the extinction of an estimated 75% of all species on Earth, including all non-avian dinosaurs. It was a dramatic, abrupt, and final change in the course of biological history, clearing ecological niches that would, over millions of years, be filled by mammals and ultimately by us. The Chicxulub impact is the ultimate case study in planetary trauma, a direct, causal link between the random mechanics of celestial orbits and the destiny of life on a world. When we watched the fragments of Shoemaker-Levy 9 strike Jupiter, we were watching a smaller gas giant version of the same fundamental physical process that, on a rocky world like ours, resets the clock of evolution. But impacts are not merely historical or planetary scale phenomena. They are also fundamental architectural forces. The very shapes, tilts, and compositions of many solar system bodies are direct legacies of colossal collisions. The unusual, extreme tilt of Uranus, spinning neatly on its side relative to its orbital plane like a rolled ball, is likely the result of a colossal glancing impact with an Earth-sized protoplanet early in its history, a blow that knocked the whole world sideways. The existence of Earth's moon itself, that shining companion, is best explained by the giant impact hypothesis, where a Mars-sized body named Theia struck the proto-Earth in its infancy, ejecting a swirling disk of vaporized debris that coalesced into our lunar companion. The heavily cratered, battered surfaces of asteroids like Vesta and Psyche tell stories of a past where such bodies were not solitary but part of a larger, differentiated parent body that was shattered by impacts, its fragments scattered. Even the rings of Saturn, those iconic bands of icy brilliance, may be the glittering debris of a destroyed moon, torn apart by Saturn's own tides or shattered in a cataclysmic collision, a necklace of destruction. The solar system, in its current arrangement, is the product of a chaotic, violent construction period where accretion through collision was the primary building tool, the hammer that forged planets from dust. The quiet stability we perceive today, the clockwork we rely on, is a temporary ceasefire in a process that is, on geological and astronomical timescales, ongoing and inevitable. This brings us back to the key, practical question illuminated, but not fully answered by the spectacle of Shoemaker-Levy. 9. Frequency. How often do events of this magnitude occur? The impact on Jupiter was a once-in-a-lifetime observational event for humanity. A stunning datum in our short history of looking, but what is its true recurrence interval in the multi-billion-year life of the solar system? Estimates based on the cratering record, on the population of comets and asteroids, and on complex statistical models, suggest that impacts releasing global-scale, civilization-ending energy on Earth happen on timescales of tens to hundreds of millions of years, rare but guaranteed over long enough periods. Impacts like Shoemaker-Levy 9 on Jupiter, involving a comet of that size, might occur every few thousand years, a regular drumbeat on the giant. But these are averages over deep time, statistical probabilities. The universe is not a metronome. It operates with a stochastic, unpredictable rhythm, subject to chance gravitational nudges. A period of relative quiet for Earth could be followed by a sudden, unexpected spike in activity, triggered perhaps by a passing star perturbing the distant Oort Cloud and sending a shower of comets inward, or by a collision in the asteroid belt, creating a new family of Earth-crossing debris. This inherent, fundamental uncertainty is what fuels the urgent discipline of planetary defense. We cannot predict the next major impact on Earth with precision, but we can work with dedication and global cooperation to ensure we see it coming decades, even centuries, in advance, and perhaps one day develop the capability to gently, precisely nudge it off course, to change our fate from passive to active. The technological and philosophical challenges of true planetary defense are immense, requiring a blend of precision engineering, deep space navigation, and long-term international commitment. Deflecting an asteroid or comet requires first detecting it decades in advance, a task that requires constant, vigilant surveying of the entire sky. Then we must precisely characterize its orbit, its composition, its structure. Is it a solid rock, a loose rubble pile? Finally, we must apply a minute but sustained force, a gravitational tractor hovering nearby, a kinetic impactor like the successful DART mission, or perhaps a focused standoff laser or ion beam to alter its trajectory by a tiny critical fraction of a degree over millions of miles. It is a task of extraordinary subtlety and precision conducted across the vast, unforgiving distances of interplanetary space. But the success of DART in 2022, which measurably changed the orbit of a small moonlet around the asteroid Didymos, proved the fundamental kinetic impactor principle works in the real environment of space. It was a first, tentative, but triumphant step toward taking an active role in our celestial destiny, a direct and courageous application of the lessons learned from being passive, awestruck observers in 1994. It marked the moment when humanity began to move from simply reading the sky to writing in it, however faintly. Yet, the quiet contemplation of impacts and our response to them leads us to even deeper, more philosophical realms. They force us to confront the sobering concept of existential risk, a threat capable of ending human civilization or even our species as a whole. While the probability in any given year, or even any given century, is infinitesimally small, the consequences over the long span of human history or our potential future are so total, so absolute, that the risk cannot be rationally ignored. This shifts impact hazards from a purely scientific curiosity to a profound matter of long-term species stewardship, a test of our foresight and our will to survive. It raises difficult questions about our responsibility to future generations we will never know, about the allocation of global resources to mitigate low probability but high consequence events, and about the intrinsic value we place on the continuity of consciousness, of memory, of culture in a seemingly indifferent cosmos. In a very real sense, the ongoing effort to map near-Earth objects is an attempt to extend humanity's timeline, to secure our tenuous foothold on this planet against the random chance of a rock from space, to buy time for our story to continue. It is an insurance policy for the species, written not in money but in telescope time, in orbital calculations, and in the silent, watchful gaze of cameras pointed at the dark. Furthermore, the study of impacts now bridges the gap between our local cosmic experience and the broader, bustling galaxy. We now know with certainty that planetary systems are common around other stars. The Kepler and TESS missions have revealed thousands of exoplanets in a staggering variety of sizes and orbits. If our own solar system's violent history is any guide, and there is no reason to believe the laws of physics differ elsewhere, then these distant systems too must have undergone their own periods of heavy bombardment and must still experience occasional catastrophic collisions between bodies. We have even begun to see potential, tantalizing evidence of such ongoing events in other star systems. In 2009, astronomers observed a strange, fluctuating light pattern from the star KC 125575448. The best explanation was a disintegrating rocky planet, its surface being vaporized by the intense heat of its close-orbiting star, creating a trailing cloud of dust, a slow-motion impact of a world with its own star's radiation. In 2021, observations of the young star Beta Pictoris suggested it may have recently witnessed a giant collision between two embryonic planetary bodies based on a sudden dimming and changes in the composition of surrounding dust. We are beginning to see with our ever-improving instruments that the fundamental processes of construction and destruction through collision that we have witnessed in our own system are universal, a common chapter in the story of planet formation across the Milky Way. Shoemaker-Levy 9 was not a freak occurrence in a quiet corner. It was a local, vivid example of a fundamental galactic process. This expansion of perspective from a single impact on a neighbor to a universal principle is perhaps the most enduring and important legacy of that July in 1994. It connected us. It connected the present moment to the deep past, showing that the titanic forces that shaped the ancient Earth and gave rise to the Moon are still at play, just on a longer, slower rhythm. It connected Earth to Jupiter, demonstrating that we share a common, dynamically rich environment populated by wandering debris, that we are all subjects to the same gravitational laws. It connected our solar system to the myriad others now being discovered, hinting that the story of planets is inextricably linked with the story of impacts, of chaos yielding to order. And it connected the human mind to the cosmos in a new, proactive way. We are no longer just inhabitants of a planet, subjects to its fate. We are, however, tentatively and newly becoming its guardians, its sentinels, looking out into the dark, using the tools of science and reason to read the trajectories of potential threats, to map the shoals in our celestial sea. The watch has begun, and it is a vigil that may last as long as our civilization itself. As we peer into that dark, we also find a haunting beauty and a persistent mystery in the very objects that pose a potential danger. Comets, like the doomed Shoemaker-Levy 9, are not just inert, silent projectiles. They are dynamic, volatile worlds in miniature, each with its own personality and behavior. To understand their mercurial nature, why they fragment, how they outgas, what drives their sudden, spectacular displays, is to understand the fundamental, pristine nature of the primitive materials from which the solar system formed 4.5 billion years ago. They are time capsules, and their violence tells us about the conditions of their birth. This contemplation leads us naturally from the catastrophic, singular drama of Jupiter's bombardment to the strange, persistent, and repetitive enigma of another icy body, one that behaves in a manner so bizarre and violently active, it challenges our very definitions of cometary behavior. Far beyond Jupiter, in the cold, sun-starved reaches between the orbits of the giant planets, in a region of space known as the realm of the Centaurs, drifts an object known as 29P/Schwarzmann-Wachmann. It is a world of perpetual, unpredictable explosion, a cosmic pressure cooker whose frequent, intense outbursts have, through careful observation, earned it the title of the second most volcanically active body in the entire solar system, after Jupiter's tortured moon Io. But its volcanoes are not of fire and molten rock. They are of ice and exotic gases, a cryovolcanism of unimaginable cold. Its story is one of internal pressure, of cryptic rhythmic triggers, and of a violently eruptive personality that we are only beginning to decipher. A story that reminds us with each sudden flare that the outer solar system is not a quiet graveyard of frozen relics, but a region of dynamic, cryogenic violence, where worlds can turn themselves inside out in a flash of cold fury. Its continued activity, a counterpoint to the singular finale of Shoemaker-Levy 9, opens a new window into the restless inner lives of these ancient icy wanderers, and in doing so brings our gaze back from the monumental to the mysterious, reminding us that discovery in our cosmic neighborhood is never complete. Good night.